Hi, I'm Eric. Thanks for the introduction. I'm a PhD student at Cornell. I'm starting my postdoc with Ishil Dillard at next week, as well as with Aditya Kella. So, okay, I'm going to talk to you about computing precise control interface specifications. And you might imagine my glee when I heard Todd's talk this morning, because we are going to be talking about networking programs. But first, let's start with the unknown. Specifically, I want to understand how we can reason about programs with unknown code. Let's start with a verification myth, a broad, general misconception that we're all guilty of. When we embark on the project of verifying a program P, that is, that it satisfies some specification phi, we assume that we have the entire text of the program P, the entire AST, so that we can use our syntactic verification technologies like OR logic or weakest preconditions. But for real code written by real engineers, software, the source code is often incomplete. That is, large portions of code are often unknown to the programmer, hidden behind libraries, module boundaries, as system calls. And so really, when we're doing this verification, our program is dependent on a set of unknown functions. So how do we ensure that our program P over these functions F satisfies our spec? Let's look at some example Pythonic pseudocode. We'll import two functions, foo and bar, from some module called unknown, whose implementation is inaccessible. In this code, parameterized on x, we'll run foo to get y, and then run bar to get z, and assert that the bitwise OR of y and z is not equal to 0. And we want this assertion to never fail. To verify this code, we're tempted to be pessimistic and sort of say, does this hold for all implementations of foo and bar? And of course the answer is no, because we can just set both of them to zeros, and then their bitwise OR is going to be 0. Okay. We could take the optimistic approach, the other extreme, and say, okay, maybe this is a very good engineer who's implemented foo and bar, and they've predicted our needs precisely. And they've managed to find some implementation, if it exists, that satisfies the spec. But this is also sort of really satisfiable. And all we've learned here is really that on one extreme, there's an implementation that satisfies the specification. And on the other extreme, there's an implementation that violates the specification. And I don't know, maybe this is interesting to you, but I'm more interested in the question of which implementations of foo and bar satisfy our specification, satisfy this assert statement. Okay, we're not the first to ask this question, so let's look at some related work. Related work has computed interface specifications that are independent. That is, they're sets of single-function conjuncts. This manifests as a conjunction of single-function first-order logic sentences where each conjunct constrains just one function from the interface. And the idea is that each function in a module should have its own specification that's distinct from the other specifications, from the other functions in that module. This Popple 16 paper called Maximal Specification Synthesis computes specs that are both safe and maximal, where maximal here means that no conjunct can be safely weakened. If we were to run our tool this tool on this example, the interface spec we would infer simply enforces that foo and bar can never produce 0 at the same time. And as we saw in our previous example where one produced all f's and one produced all zeros, that's sort of overly restrictive for this example. On the flip side, we could err on the other extreme and follow this approach using necessary preconditions from SIGCOMM 2020. And a necessary precondition is this Cousseau and Cousseau idea from VMKI 13, where you try to eliminate no good runs from the program. And in this case, there's actually no way to eliminate no good runs, eliminate also satisfy our syntactic requirement. So we just infer true here. Or this tool just infers true. And of course, this is not safe. This is wildly permissive and also not going to give us any good information. So it seems that as far as related work goes, engineers have to make a trade-off between the permissiveness of their specifications and their safety. We aim to have the best of both worlds. So for a program with functions f that want to satisfy our specification, our goal is to compute an interface specification for these f's that is safe, of course. It prevents any bugs that might occur. And it's also maximally permissive. And we're going to unify both of these concepts into a notion called precise, which just means that the set of functions f satisfies the interface specification if and only if using that implementation in the program p satisfies phi. We're also going to have this notion of efficiency of specifications, but we'll discuss that in more detail later on. So let's see what a precise spec looks like for our example program. In this example, we can easily compute it by starting with the assertion and working backwards, substituting in our function invocations. And hopefully that's convinced you that this specification is actually equivalent to the program that we had before. This spec improves on previous work because it is safe and maximally permissive, and it's also weakest, which you can approximate for now as just meaning that there's no unnecessary variables, there's no unnecessary stuff going on here. So what can we do with the spec? Well, we usually think of specs as being these human-written objects that we can use for things like documentation or manual verification. But computed specs are often not human-readable. They're often comprised with lots of machine gobbledygook that's hard for humans to parse. But that makes them also great for automated verification, because computers can actually understand all of their own gobbledygook. So in this paper, we'll focus on the specific use case of computer networking. We heard from Todd earlier about how verification in the networking domain is flummoxed by unknown, by these dynamically configurable pieces of information. He focused on verifying the control plane protocols like BGP or OSPF, but in general, the control plane can be some sort of bespoke, say, software-defined networking piece of software. And here we're going to peel back one layer of abstraction, and rather than focus on these protocol-level bugs that Todd was talking about, we're going to focus on program-level bugs in the data plane pipeline. So if you were at the keynote, you heard talk about these forwarding tables, which are computed dynamically at runtime to correspond to changing network conditions. And these serve as the unknown functions that are plugged into these data plane pipelines. However, as is common in systems design, the set of tables that we can syntactically express is much greater, is much more permissive than the set of tables that the data plane pipeline can actually handle. And so if we can precisely capture the permitted configurations using an interface specification, then we can improve the robustness of the network. For example, by producing a runtime monitor that rejects buggy configurations, or using them as an input to a tool like Batfish. So this is where our work, Capiche, fits in. Capiche computes control interface specifications, ci-specs, that are precise, which means they're both safe and maximally permissive, and also efficient to check. Let's jump into how we do this. Our first step is to define an abstract model of pipeline programs. And for expositional purposes, we'll jump into the middle of the pipeline, where we use Dijkstra's guarded command logic, a modern version of it, over a set of uninterpreted functions f that model these unknown table configurations. A GCL program has a bunch of variants. The first is assumption, where we assume some formula phi, which we're going to elide the details, but if you know what these things mean, it's a formula in the quantifier-free theory of fixed-width bit vectors. Bit vector arithmetic, Booleans over it with comparison, signed-unsigned comparison, no quantifiers. So we can make assumptions about our code. We can also change the state of a networking packet by assigning to its variables, assigning bit vector arithmetic expressions to its variables, which of course we're going to elide that grammar, but we are going to specifically pull out that we can have uninterpreted functions on bit vectors here. Again, these are how we capture the unknown. We also have sequential composition, which is standard, and this box operator is non-deterministic choice, which I'm not going to go into the details of that, but let's look at an example just to get a sense for how it works. We can encode an if statement into GCL by thinking of if phi then C1 else C2 as syntactic sugar for this GCL program, which non-deterministically runs these two programs. The program on the top assumes phi and then runs C1, and the program on the bottom assumes the negation of phi and runs C2. And what's important here is that non-deterministic choice is optimistic with regard to assumptions. Rather than crashing, like an assert statement might, when an assume is violated, we are only going to execute those branches that have satisfied assumptions here. In this example, since phi and not phi are disjoint, we're going to run only one of them for any given input. Okay, so we have this model. And we can rely on largely standard techniques to compile the program into first-order logic. Our first step is lifting, and we're going to elide the details, but the basic idea is that we can produce a formula that lifts out all of our uninterpreted function invocations and leaves us with a GCL program with no uninterpreted functions over our original set of variables that's synchronized using a set of configuration variables. We can use this program to symbolically produce our first-order logic specifications. We use standard symbolic compilation algorithms from Flanagan and Sachs 2001, or if you're not familiar, you can think of this as just Dijkstra's weakest precondition. And this gives us a formula that looks like this. We have phi over our packet variables and our configuration variables. But importantly, the packet variables are universally quantified because those data plane variables, just like in Todd's talk, are not available for static analysis. So this is a precise ci-spec. We're almost ready to declare victory. But the problem is that this kind of a specification is not efficient to monitor. And the basic notion is that this set of packets is giant. The set of possible, there are maximum 1,500 bits in a networking packet, which means that if we were to actually think about all of the packets in this finite domain, that would be 2 to the 1,500, which is more than there are atoms in the universe. So we're not going to do that. What we're going to do instead is quantifier elimination. We're going to eliminate this packet variable from the thing that we have to check about our implementations. So basically, we eliminate our quantified variable about the data plane. And this gives us an equivalent specification to our original quantified formula. And this is our precise and efficient ci-spec. We prove in the paper that it is precise, which means that it is both safe and weakest. It's efficiently monitorable. When we characterize this formally by defining a syntactic class of first-order logic sentences and showing that they have polynomial expression complexity. And of course, it's decidable because our domain of quantification is finite, but very, very intractably large. So our solution is to use a precise path-based decomposition. We start with a sufficiency check that generates counterexample paths when it fails that we can use to we can hyper-optimize these paths because paths are very easily compressible. And this generates a very small QE instance. We'll pass this to our solvers, which will help us to generate a new candidate specification. And we'll continue this loop until eventually our sufficiency check succeeds. To see how well this works, we collected a suite of industrial and academic P4 programs. P4 is a language for writing these data plane programs. And we checked a standard safety property that's akin to no null pointer dereferences. And for this property, Capiche computes CI specs for most programs in a matter of seconds or minutes. But a few of them hit our 24-hour timeout. But do not worry. Capiche's timeout here actually gives us valuable information about the code. After inspecting these programs closely, we found bugs in the code and in their interfaces. And after fixing them, we could compute specifications in hours or minutes. This has led us to hypothesize that long Capiche runtimes can be considered a kind of code smell, a suspicious observation that likely indicates buggy behavior or poor design. We also checked defined forwarding, which just means that that every packet's forwarding behavior, either that it's dropped or sent out on a specific packet, is defined at the end of processing. And we can do these in just a few seconds to a few minutes. In our paper, you can see our quantitative analysis of our path-based heuristic, as well as our improvement over previous work in the data plane specification inference space. Notably, at the cost of some runtime, assuming our CI specs makes more bugs unreachable than previous data plane spec inference published at SIGCOMM. So let's jump back. We started worried about the unknown and how we can reason about programs in an interesting way with unknown or missing code. Now, with Capiche, we can tame the unknown using a precise CI spec, which precisely describes the implementations of the functions f that cause the program to satisfy its spec. Thanks. I'll take your questions.
Any questions? So maybe let me first ask a simple question. So yeah, I think it's like a wonderful idea to infer such kind of precise specific specs from the data plane programs. But what kind of programming features of this networking or data plane program can make it efficient or to make all the work possible? Because the full pipeline, it seems that it also works for general programs.
Yeah, so that's a great question. I can rephrase. What about data planes makes this work? So there's a bunch of features that data plane pipelines have that make this simpler. One of them is tables can only occur in sort of linearly. So a table only occurs, functions only occur once syntactically in the program, which gives us more efficient specifications than we would have if they could interact more freely. Another is that they're loop-free programs over a finite domain, which means that we don't have to infer loop invariance, we don't have to worry about complicated loops or anything like that when we generate our verification conditions. And they're over a finite domain, which means that we can do quantifier elimination. So presumably, this kind of approach could work over any domain that admitted quantifier elimination. But I'm not willing to swear to that. That's just an intuition. So yeah, thanks.
Okay, thanks.
Yeah, this is really cool. So as I understand it, packets are like flat big vectors, right?
Yes, yeah, they're bits that you extract from the wire, and then languages like P4 parse them into basically structs that you can use more programmatically.
I see, yeah. So my question is like, is there opportunity to kind of give structure to those flat bit vectors for better verification performance by maybe assuming some faceted parsing or something?
That's actually what makes our compiler optimizations work so well. We can do things like dead code elimination, expression propagation in order to sort of basically do a program level quantifier elimination pass by reducing the size of the program, reducing the number of variables in the program, so that the thing that we actually have to symbolically compile is very compact.
So what you're saying is if by doing QE, you're kind of imposing structure that you discover on the
Yeah, exactly, because it's the structure gets a little bit obfuscated when you turn it into a formula.
Great, thank you.
Anyone want to ask a question? Maybe I just ask one more question about the evaluation. So can you go back to the kind of efficiency about the tool?
Oh, this one? Or this one?
Okay, the problem is that, this one. So how efficient would, how large are the benchmarks and
the programs can be pretty large. These are sort of real industrial grade P4 programs that comprise thousands of lines but have quadrillions of paths through the program. And in our experience, it seems like the number of paths through the program is really what causes performance degradation, not necessarily the length of the code. Because the number of paths through the program determines, especially for things like defined forwarding or no null pointer dereferences, you have to analyze all the ways that you could create valid data or invalid data. And that's really dependent on these complex parsers, which we'll hear about in a couple talks, and how they, in a complicated way, produce data. So it's really the number of paths through the program that makes this more complicated, because that sort of correlates to the number of counterexample executions that you have. But the point is that our path-based heuristic means that we're only exploring a very, very small proportion of those paths, many, many orders of magnitude smaller.
Okay, I see. Thanks.
Yeah.
Yeah. So I think then thank Eric again for the wonderful talk. And
thank you.